A team of researchers from Freiburg University has succeeded in developing artificial muscles that take advantage of natural processes in the body. Artificial yarn muscles, 100 times stronger than humans, could be used to create humanoid robots with Terminator-like strength using just ordinary fishing line and sewing thread. A team of international scientists has found a way to turn them into artificial muscle. Want to know about it? Well, stay tuned to the video and watch the video till the end. Hello guys, welcome to Futureality. Hit the subscribe button and turn on the notifications to get new updates about technology and development. Hit the like button to show your support, and in today's video we're going to discuss, in the near future scientists will create artificial muscles stronger than natural muscles. So without any further ado, let's begin. Dr. Stefan Schiller and Dr. Matthias Huber from the University of Freiburg have created a muscle purely out of natural proteins. Scientists have recently created artificial organs, such as a pancreas, which is helping diabetes patients manage their condition. However, the artificial pancreas is reliant on AI and technology. This new discovery is one of the first forays into fully organic creation. These artificial muscles could be used in prosthetics, micro-robots, and even smart textiles that respond to environmental changes, the researchers said in the papers. Mehmet Kanik of the Massachusetts Institute of Technology and his team created a two-phase polymer fiber that was used to create artificial muscles that are activated by heat and can lift for more than 650 times their own weight. The muscle could also withstand strains of more than 1000%. The researchers tested the muscle in an artificial bicep. It lifted a weight when the heat was applied to it. Artificial muscles are particularly suitable for human-machine interaction applications because of their soft and tough mechanical properties, flexible drive mechanisms, low fabrication complexity, and acceptable efficiency at a miniature sub-centimeter scale. In recent years, artificial muscles have developed rapidly, driven in part by new and improved materials, fabrication processes, and device structures. There has been an increasing amount of literature on artificial muscles based on a variety of actuation mechanisms, such as small-scale pneumatic, dielectric, elastomer artificial muscles, ionic polymeric actuator, micro-piezoelectric actuators, magnetic actuators, and actuators based on shape memory alloys and polymers. Since it derived from the naturally occurring protein elastin and is produced by us through biotechnological means, our material is marked by a high sustainability that is also relevant for technical applications, said Dr. Schiller. In the future, the material could be developed further to respond to other stimuli, such as the salt concentration in the environment, and to consume other energy sources, such as malate derived from biomass. Pioneering the technique was nanotech expert Ray Bauman of the University of Texas at Dallas and colleagues, who demonstrated the principle on standard household materials. The muscle designs could have various applications, including robotic body parts, as built into the fictional cyborgs the Terminators pictured. They used a chemical energy source as fuel, sodium sulfide. In an oscillating chemical reaction in which the pH changes in cycles due to a special linkage of several reactions, the added energy was converted into mechanical energy via non-equilibrium states of the material. Natural muscles still have one key advantage over their synthetic counterparts. However, they're considerably more efficient. Even the most advanced artificial muscle is only able to convert around 3% of the energy that is put into it, Professor Tawfik told New Scientist. The rest of the energy is lost, having been accidentally converted into heat. Should engineers succeed in mitigating this problem, however, the prospective applications for artificial muscles are manifold, allowing for the creation of cheap and compact replacements for the bulky electrical motors of the present day. The mechanism is as flexible as an octopus, as strong as an elephant, and as fast as a hummingbird. With this technology, the team is hoping to eventually engineer full-body robots that can gracefully mimic human movement. We have basically taken the best of those two approaches and merged them into a new technology, says senior author Christoph Keplinger, a mechanical engineering professor at CU Boulder. The movement-creating device is called a hydraulically amplified self-healing electrostatic actuator. The pump-free devices are pouches made of the same inexpensive plastic that makes up potato chip bags and filled with an electrically insulating liquid similar to canola oil. The device changes shape when voltage is run through them, and the malleable oil gives the mechanism the potential to self-heal. Muscles form an intricate network of sinews throughout the body of animals. They respond to electrical stimulation, which is carried from the brain to the muscle via nerves. There are different types of muscle, which are often made of different types of tissue. For example, the heart, which never stops beating, is made of a different material to skeletal muscle. Skeletal muscle is attached to one end of a bone. It stretches all the way across a joint, the place where two bones meet, and then attaches again to another bone. Skeletal muscles are held to the bones with tendons. Once the electrical signal reaches the muscle, it triggers a contraction. This is done by two types of protein overlapping and working against each other. A thick filament is composed of the protein myosin, and a thin filament is composed of the protein actin. Muscle contraction occurs when these filaments slide over one another in a series of repetitive events. However, many of these artificial threads respond to their stimulus very slowly due to their large size or complex actuation processes. When fibers can respond quickly, there's a trade-off in size or quality. Animal muscle fiber exhibits superior mechanical properties and actuation performance, said senior author Chengqiang Kai, associate professor of mechanicals at the University of California, San Diego. Only a few existing materials show similar actuation behaviors as animal muscle, and the fabrication of fibers from those materials with a size and quality comparable to muscle fiber is not easy. Elon Musk's Neuralink, the secretive company developing brain-machine interfaces, showed off some of the technology it has been developing to the public for the first time. The goal is to eventually begin implanting devices in paralyzed humans, allowing them to control phones or computers. For Musk, the central problem of interacting with AI is actually bandwidth. The first big advance is flexible threads, which are less likely to damage the brain than the materials currently used in brain-machine interfaces. You can take in information much more quickly than you push it out via your voice or thumbs, but you're already connected to a machine, an idea most closely associated with philosopher Andy Clark. Hence, his goal is for this system to allow humans to more quickly communicate with machines directly from their brains. These interfaces involving decoding brain signals from the surface of the skull through EEG or via implanted electrodes and then translating those signals into a motion command for a robot or cursor. There has also been some progress made in the other direction, using external electrical signals to stimulate the brain. Although medical applications are driving the research, there are also commercially available playthings that allow for novelties such as mind-controlled drone racing. Still, they are a long way from Elon Musk's vision of symbiosis between man and machine, which would require a much more granular understanding of the brain network that goes beyond the basics of motor control to more complex cognitive facilities like language and metaphor. A monkey has been able to control a computer with its brain. It's not going to be suddenly Neuralink will have this neural lace and start taking over people's brains, Musk said. Ultimately, he wants to achieve a symbiosis with artificial intelligence, and that even in a benign scenario, humans would be left behind. Hence, he wants to create technology that allows merging with AI. He later added, "We're a brain in a vat, and that vat is our skull, and so the goal is to read neural spikes from that brain." The theory is that with sufficient knowledge of the neural activity in the brain, it will be possible to create neuroprosthetics that could allow us to communicate complex ideas telepathically or give us additional cognitive extra memory or sensory night vision abilities. Musk says he's working on an injectable mesh-like neural lace that fits on your brain to give it digital computing capabilities. Now that we've come to the end of this video, I want to thank you for sticking with me, and I'd love to know what you think of it. Just comment down below. Also, if you like this video, make sure you like it and stay safe. Today's video is over, but if you want to see more, there's one on your screen right now, and there are a few more fun videos coming soon. I'll see you in the next video.